Howdy. So what have we learned? We've learned that Lewis diagrams enable us to determine the number of bonding electrons, non-bonding electrons, and bond orders for a compound. We've learned that when doing Lewis electron dot diagrams, we have to make sure we use the right number of valence electrons. So we calculate the number of valence electrons at the very beginning. We don't care where the valence electrons came from, and then we try to redistribute the valence electrons, trying to make the most stable structure possible. We've learned that Lewis diagrams are primarily used for S and P block elements. And we've learned that Lewis diagrams are one of these essential tools that all chemists use. And as long as you're going to do chemistry, you're probably going to use Lewis diagrams. So it's something that you should learn how to do very well. Now this video is on oxidation states, formal charges, and exceptions to the octet rule. And so oxidation states are used to track electrons to tell which element lost or gained an electron during a reaction. Formal charges are used to tell which Lewis electron dot diagram is the most stable. The lower the formal charges, the more stable the diagram. Now we had been using the concept of the noble gas to determine if a Lewis diagram was stable. Using formal charges often can be more accurate. Now we'll see that sometimes it's better to still use noble gas configuration. Often though, Lewis formal charges is a better way of looking at it. And so using formal charges, we can actually understand why there's exceptions to the octet rule. Now after watching this video, you should be able to determine oxidation states and formal charges of atoms in a molecule. Using formal charges, you should be able to determine which resonance structure is the most stable. Using formal charges, you should be able to understand why there are exceptions to octet rule. And also we'll see with formal charges, we can understand what types of environments different types of elements find stable. And so atoms and molecules are often characterized by oxidation state or oxidation number. I'll use oxidation state and oxidation number interchangeably, or by formal charge. Now the oxidation number is the charge an atom would have if the bonds were purely ionic. Formal charge is the charge an atom would have if the bonding electrons were equally shared. Okay, so please remember, oxidation number, we're assuming bonds ionic. Formal charge, we're assuming bonds purely covalent. Now we can determine the oxidation number of an atom and molecule by doing the number of valence electrons of the atom by itself. And so that's actually just the column number in the periodic table, minus the number of valence electrons in the bound atom with the bonding electrons going to the most electronegative, or assuming that the bonds were ionic. Now, alkaline metals in a compound will typically have a +1 oxidation number. Alkaline earths in a compound will typically have +2. Oxygen will be typically -2, and fluorine will be typically -1. So if we look at water, and we assume the bonds are purely ionic, again, because we're doing oxidation number, and oxidation number is the charge an atom would have if the bonds were purely ionic. Oxygen is more electronegative. It has a larger electronegativity, and so the bonding electrons go with the oxygen. And so the hydrogen is actually left without any valence electrons. And so now using the equation, number of valence electrons by itself, and so oxygen's in the 6th column, so that's where that 6 comes from, minus number of valence electrons in the bound atom with the bonding electrons most electronegative, and so we see 2, 4, 6, 8, and so 6 minus 8 gives us an oxidation number of -2 for the oxygen. For the hydrogen, it's in the 1st column, so number of valence electrons atom by itself would be 1. Now, because we assumed the bonds were purely ionic, it lost any electrons, and so 1 minus 0 gives us a +1. And so we would say that the oxidation number or oxidation state for oxygen was -2. The oxidation number or oxidation state for hydrogen would be a +1 in water. Now the sum of oxidation states is equal to the net charge. And so -2 + 1 is equal to 0 because water has no net charge. And so it gets kind of confusing sometimes. When we are talking about noble gas configuration, we would say that hydrogen sees 2, and so we'd count these 2 for the hydrogen. We'd see the oxygen sees 8, so we'd count all 8 for the oxygen. And then when we're calculating oxidation number, the bonding electrons goes to the most electronegative, and so now hydrogen in the compound sees 0, and oxygen still sees the 8. Now the equation to determine oxidation number and the equation to determine formal charge is very similar. The first part is exactly the same. Number of valence electrons of the atom by itself, number of valence electrons atom by itself, minus, for oxidation number, number of valence electrons in the bound atom with the bonding electrons most electronegative, because again, oxidation number, charge if bonds were ionic. But for formal charge, it's number of valence electrons in the bound atom, the bonding electrons equally shared, because the formal charge is the charge an atom would have if the bonding electrons were equally shared. And so they look very similar, but this last term here is a little bit different. And so if we determine the formal charge of the atoms in water, because we're doing formal charge and we're assuming the bonding electrons are equally shared, and so we have these two bonding electrons, and we give one to hydrogen and we give one to oxygen. Now we use the equation. So again, oxygen's in the 6th column, so it has 6 when it's atom by itself, minus 2, 4, 6. And so that gives it a formal charge of 0. For hydrogen, it's in the 1st column, so atom by itself is 1. And now it has 1 here, assuming the bonding electrons equally shared, and so 1 minus 1 gives us 0. Now, just like for the oxidation states, the sum of the formal charges has to equal the net charge, which in this case is 0. And so again, formal charges closest to 0 is most stable. And so I would say that the Lewis diagram that we wrote here should be stable. Everything has noble gas configuration. Everything has formal charge as 0. And so that should be 0. And again, it's a little confusing. When we talked about noble gas, we included these two. For the hydrogen, said it saw 2 electrons, so that's the noble gas for helium. The oxygen, we said, saw 8 electrons, so that's noble gas configuration. And then when we're calculating it for formal charge, or when we're calculating formal charge, we split those bonding electrons. Oxygen keeps its lone pair, and so we see the hydrogen with 1, oxygen with 6, and that hydrogen with 1. And so again, we can try again. This time we have CO2, and so for oxidation state, we assume the bonding electrons go to the most electronegative. And so oxygen is more electronegative than carbon, and so the oxygen gets all 4 of the bonding electrons. Carbon gets nothing. Oxygen, all 4 of those bonding electrons. And so now for the oxidation number, it would be 6 for the oxygen, minus 2, 4, 6, 8. And so that gives us a minus 2. For the carbon, it's in the 4th column, so it starts with 4. The number of valence electrons in the free atom is 4, minus 0, because right now it has 0, and so that gives us a plus 4. Now again, the sum of oxidation states equal to that charge, so minus 2 plus 4 gives us oxidation state of 0. Now for the formal charge, we assume the bonding electrons are equally shared. And so now for these, 2 goes to the oxygen, 2 goes to the carbon. These 4, remember each line represents 2 electrons, to the carbon, to the oxygen. And so for the oxygen, 6 minus 2, 4, 6, that gives us a formal charge of 0. For the carbon, 4 minus 4 gives us a formal charge of 0. And so again, that indicates that this Lewis diagram should be relatively relatively stable. Everything has noble gas configuration. Everything has formal charge of 0. And again, a little confusing. When we're talking about noble gas configuration, we say the oxygen sees 2, 4, 6, 8. So we see all 8. When we're calculating the formal charge, we're splitting those bonding electrons. Carbon gets 2, and the oxygen gets 2.
Are a way of keeping track of the electronic charges in molecules. They are calculated as the number of valence electrons associated with the free atom, minus the number of electrons associated with the atom in a molecule or ion. The rules for calculating the number of valence electrons in a molecule are illustrated by the example of HCl. Unshared electron pairs are assigned entirely to the atom carrying them, and shared electron pairs are assigned equally to the 2 atoms sharing them. The free hydrogen atom has 1 valence electron. The formal charge on hydrogen in HCl is calculated to be 0. The free chlorine atom has 7 valence shell electrons. The formal charge on chlorine in HCl is also calculated to be 0. Notice that the formal charge on both atoms in HCl is 0. Remember that the formal charge is not an estimate of the actual charge on the atoms. We know that in HCl, the chlorine bears a partial negative charge because it is more electronegative.
And so we're able to calculate the formal charges for the hydrogen and chlorine. Again, please remember formal charges are the charge an atom would have if the bonding electrons are equally shared, or if all the bonds were purely covalent and yet equal sharing.
Formal charge calculations can often help us identify the most stable isomers of molecules. Consider the isomeric compounds, hydrogen cyanide and hydrogen isocyanide. Both structures have octets of electrons about carbon and nitrogen. The formal charge on carbon in hydrogen cyanide is 0. Similarly, the formal charge on nitrogen is 0. In hydrogen isocyanide, the formal charge on carbon is -1. The formal charge on nitrogen is +1. Because the formal charges are non-zero in hydrogen isocyanide, we can predict that this isomeric form is less stable than hydrogen cyanide, as found to be the case.
And so formal charges are very important in determining which structure is more stable. And so we have two isomers. Now isomers just mean you have the same exact set of atoms, but you could have different arrangement or different bonding. And so if we look at the one on the left, noble gas configuration, carbon has noble gas at Cs8, nitrogen has noble gas at Cs8, noble gas has Cs2, nitrogen Cs8, and carbon Cs8. So for these two isomers, according to noble gas, we'd say that they're equally stable. Now if we look at the formal charge, the one on the left, everything is 0, but here we have non-zero values. And so formal charges of 0 we want the predominant structure to be formal charges of 0 as much as possible. And so the one on the left should be more stable, the one on the right is less stable.
Formal charges can also be helpful in evaluating alternative resonance structures. Let's consider nitrogen dioxide, a molecule that contains an odd electron. We can draw two reasonable Lewis structures, but which more closely describes the nitrogen dioxide molecule? Notice that in one structure the unpaired electron is on oxygen, and in the other it's on nitrogen. In the first structure, the formal charges on all the atoms are 0. In the second structure, nitrogen bears a formal positive charge, and one of the oxygens bears a formal negative charge. Nitrogen is less electronegative than oxygen. Nevertheless, a formal positive charge on nitrogen and a formal negative charge on oxygen is an indication that this resonance structure contributes less to the ground state structure of NO2 than the previous one, with the unpaired electron on oxygen.
And so if we look at these structures, well, if we count the number of valence electrons, so oxygen starts with 6, we have 2 of them, so that's 12, plus 5 gives us 17, 2, 4, 6, 8, 10, 12, 14, 16, 17. And so we have 17 valence electrons. That's an odd number. And so it means not all atoms will have a noble gas configuration. If we look at oxygen here, 2, 4, 6, 7, it sees 7 valence electrons. Now, we have 7 here, and so the question is, this one also sees 2, 4, 6, 7. The nitrogen sees 7. Which is more stable, to have nitrogen with 7 or oxygen with 7? And so we can actually figure this out by calculating the formal charge. And so here we have formal charges all 0. Here we have a formal charge of +1 and -1, and so this one should be less stable. Now we say that the actual structure is a weighted average of all resonance structures. What that means is that if a resonance structure is less stable, then the actual structure will be a little bit less like that structure. Okay, if the two resonance structures have equal energy, then the actual structure is going to be an average of those two resonance structures. If one of the resonance structures is less stable, then the actual structure is going to relate to that less stable structure a little bit less. And so the one with the formal charge of 0 is going to be extra stable or more stable. And for formal charges, they're really kind of cool. We can actually use them to determine which type of environment is more stable. And so here we have boron, and boron has 3 valence electrons. And so we can actually calculate the formal charge for this first environment. And so we have 3 minus 1, 2, 3, 4. Now it's kind of cool. For formal charges, it doesn't matter what the thing is bound to, right? Because you're assuming the bonding electrons are equally shared. And so you know that boron with 4 single bonds should have a formal charge of -1. Now for the next one, we have boron, so 3, remember, valence electrons of the free atom, boron's in the 3rd column, minus 1, 2, 3, 4, 5. So that gives you a formal charge of -2. And this would be -3, -4. Now notice down here, we actually have 3 minus 1, 2, 3. Remember, it gets half the bonding electrons, so there's 2 bonding electrons here. Boron gets 1 of those, 1 of those, 1 of those, so 3 minus 3 gives us 0. This would be 3 minus 4, 3 minus 4, and then 3 minus 1. And so what this tells us is that boron often likes to have just 3 valence just 3 single bonds. And so notice that according to the formal charge, this is a stable environment, even though it does not follow the octet rule. And so this is one of the exceptions to octet rule. You know, in the last one we saw that for radicals where you have an odd number of electrons, that's an exception to octet rule. If you have an odd number of electrons, you cannot have octets for everything. Now here's our second exception to the octet rule, in that we have boron often likes just 3 single bonds, and that will not give it noble gas configuration. But again, this is very helpful. We can see what environments are more stable for the different elements. For carbon, with 4 single bonds, so carbon's in the 4th column, minus 1, 2, 3, 4. Remember, it gets 1 electron for each of these bonds, and so that gives you 0. And so this should be a stable structure for carbon. Carbon would be happy with 4 single bonds. Doesn't really like a double bond, doesn't really like a lone pair, doesn't like 2 lone pairs or 3 lone pairs or 3 single bonds. But again, we find that it likes 2 singles and a double, or 2 doubles, or a triple and a single. And it's kind of interesting for carbon, its stable environments would be 4 singles, 2 singles, a double, 2 doubles, a triple, and a single. And so carbon typically does not like having a lone pair. One exception would be carbon monoxide, but there you have that triple bond, which is why carbon monoxide is fairly stable. We can do nitrogen, and so again, nitrogen's in the 5th column, and so for 4 single bonds, 5 minus 4 gives us a +1. And remember, when you're doing the formal charge or oxidation number, the atom keeps its lone pair, and so 5. And notice that all these, you start with the 5 because that's the number of valence electrons for the free atom. And so 5 minus, it keeps its lone pair, 2, 3, 4, 5. 5 minus 5 gives us 0. And so that's a stable structure. And so what we see is that nitrogen typically wants 1 lone pair. That will give it a stable configuration. For oxygen, with 4 singles, you get a +2, so that's not very stable. And if we continue, and so here we have, remember, oxygen is in the 6th column, and so we start with 6 always because we're talking about valence electrons for a free atom, minus, it keeps its lone pair, 2, 4, 5, 6. And so this gives you a formal charge of 0, so that means this should be a fairly stable environment for oxygen, and this is a fairly stable environment for oxygen. If we do fluorine, so fluorine is in the 7th column, and so 7 minus 4 gives us a +3. Now it's kind of interesting for fluorine, you only have 1 really stable environment. And so fluorine typically has 3 lone pairs and a single bond. And so again, 7th column, so 7 valence electrons for the free atom. That's where that 7 comes from. Minus, it keeps its lone pair, 2, 3, 2, 4, 6, 7. splits that bonding, and that gives us 0. Formal charge is 0, is extra stable. And so looking at that row, we can actually determine what is the most stable configuration for these elements. Now it's really kind of cool when you're doing Lewis diagrams. Keep these in the back of your mind, and it makes doing Lewis diagrams a little bit easier. Okay, so when you're starting with carbon, typically think carbon wants 4 singles, 2 singles and a double, 2 doubles, or your triple single. When you're thinking about nitrogen, remember nitrogen typically wants a lone pair. Oxygen wants 2 lone pairs. Fluorine wants 3 lone pairs. And again, please remember boron is an example for an exception to the octet rule. It often doesn't have an octet. It's actually happy with 6 valence electrons. Now if we look at sulfur, which is a row down, now elements in the 3rd row and lower can actually have more than 8 valence electrons. And so sulfur can have more than 8 valence electrons. Now if we count or determine the formal charges, it's kind of interesting. We see that here's 3 environments with formal charges of 0. And so that means this is going to be a stable configuration for sulfur. And again, remember, 3rd row and lower, you can have more than 8 valence electrons. And so this is another exception to the octet rule. Here sulfur is surrounded by 2, 4, 6, 8, 10 valence electrons. Sulfur is in the 6th column, so that's why we start with the 6 minus 2, 3, 4, 5, 6. Formal charge is 0. But you cannot do this with oxygen because oxygen is in the 2nd row, and so it cannot have more than 8 valence electrons. And so we can see that formal charges rationalizes some of the exceptions to the octet rule, right? We saw boron with 6 valence electrons, 3 single bonds was stable because it had a formal charge of 0. We see that sulfur, sometimes with more than 8, gets a formal charge of 0 and is also stable. Now xenon does form a few compounds. It's below the 3rd column, below the 3rd row, and so it can have more than 8 valence electrons. It's kind of a cool molecule to do Lewis diagrams with. And so remember that noble gases except for helium have 8 valence electrons. That's why we have 8 there. They're in the 8 columns. And so stable environments for xenon would include 3 lone pairs, 2 single bonds, or 4 single bonds and 2 lone pairs. And so we got 8 minus 1, 2, 3, 4, 5, 6, 7, 8. So that's the formal charge of 0. Even though we'd say that the xenon was surrounded by 2, 4, 6, 8, 10, 12 electrons. Elements in the 3rd row and lower can have more than an octet. And so these are the most stable configurations for sulfur and xenon. I think I probably left off a couple. And again, we understand that these are stable based on the formal charge, and that elements in the 3rd row and lower can have more than 8 valence electrons. This is for the 2nd row. And so again, boron is another exception to octet rule. It is happy often with just 3 valence electrons. And so we had talked about carbon dioxide before, and we used the formal 2 double bonds to actually draw the Lewis diagram. And notice that each of these has formal charge of 0. So you have 6 minus 2, 4, 5, 6 gives us 0. And for the carbon, you have 4 minus 1, 2, 3, 4 gives us formal charge of 0. That's kind of interesting. We could have tried to have a triple bond and a single bond. And this would still be an octet, still be an octet, still be an octet. And so based on noble gas configuration, this looks completely fine. But if we do the formal charges, we have 6 minus 2, 4, 6, 7. And so that would give us a formal charge of -1. For the carbon, 4 minus 4, that'd be fine. For this oxygen, 6 minus 2, 3, 4, 5 gives us a formal charge of 0. And so what that tells us is that, we have 2 resonant structures here. This one, you have formal charges of 0, and so this one should be the more stable one. It's the predominant resonant structure. We could also look at other structures. How do we know the carbon is in the center? Well, if the oxygen was in the center, well, again, we can do it with the formal charges, and we see if we don't have the carbon in the center, then we get formal charges not as 0. Likewise, what is the most stable structure for N2O. And so if we really want to do that, we have to do the formal charges. And so we calculate the formal charges, and we have to find the one closest to 0. And the other thing I should mention is that we not only want the one closest to 0, so we notice that these with 2 aren't going to be good, and so that leaves us these 2. And so how do we differentiate between these two structures? Well, you want the more electronegative atom to have the negative formal charge. So oxygen is more electronegative than nitrogen, and so that tells you that the structure on the right should be a little bit more stable because the negative formal charge is on the most electronegative atom. You could also be asked, what is the most stable Lewis diagram for sulfur dioxide? And so sulfur has 6 valence electrons, oxygen 6. 3 times 6 gives us 18. So we have 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14, 16, 18. So we used 18 valence electrons. We can imagine this. This has noble gas, noble gas, noble gas configuration. So all the atoms in both these Lewis diagrams are noble gas configuration. And so let's use the formal charge. And using the formal charge, we see that the one on the right should be the more stable structure. Now that also makes sense because thinking about it, the sulfur-oxygen bonds should be identical. Another thing to remember is that oxygen with 2 lone pairs and a double bond has a formal charge of 0, and oxygen with a single bond and 3 lone pairs has a formal charge of -1. And so doing Lewis diagrams of compounds that contain oxygen, it's again very helpful to remember 2 lone pairs and a double bond, formal charge is 0. 3 lone pairs and a single bond has a -1 formal charge for the oxygen. And so formal charges often is better or more informative than just noble gas configuration. Both the structures all the atoms have noble gas configuration, but the one on the right has formal charge of 0, so we know that one must be more stable. So we could also ask about sulfur trioxide. Now, what I'm thinking is when I have an oxygen-containing compound, I'm thinking about my oxygen, and I typically want a double bond and 2 lone pairs because I know this has a formal charge of 0. I know this has a formal charge of -1. That has a formal charge of -1. And so typically when I'm doing Lewis diagrams of oxygen-containing compounds, I like to start here if that center atom is in the 3rd row and lower. Remember, 3rd row and lower can have more than an octet. And so now if we calculate the formal charges of all the atoms in these 3 Lewis diagrams, we see that sulfur here is a +2. I should also mention that 4 times 6 gives us 24 valence electrons, and so each of them has 24. And so if we look at the formal charges, we see we have a +2. And so this is farthest from 0, so the one on the left should probably be the least stable resonance structure. And the one on the right is the most stable because we have zeros. And again, elements in the 3rd row and lower can have more than an octet. And so that tells us the one on the right is the most stable structure. And so sulfur trioxide looks something like this. Again, the sulfur and oxygen bonds should be identical. If we look at BF3, we can imagine, so we have, let's see, boron has 3 valence electrons. Each fluorine has 7. 3 times 7 is 21, plus 3 gives us 24. And so this has 24 valence electrons. This has 24 valence electrons. Now here, everything has noble gas configuration. Right, you have 2, 4, 6, 8, 2, 4, 6, 8. Boron has noble gas configuration. And so based on noble gas configuration, you might think the one on the right is more stable. But once we calculate the formal charge, we see that we have a -1 formal charge for the boron and a +1 formal charge for the fluorine. And so in this case, the formal charge is a better indicator of stability. And so the structure on the left is more stable. And so again, we've seen 3 exceptions to the octet rule. When you have an odd number of electrons, you have a radical. You can't have everything noble gas configuration. Elements in the 3rd row and lower can have more than 8 valence electrons, so they can violate the octet rule, and boron and aluminum are often happy with just 6 valence electrons. And so these are our 3 exceptions to octet rule. Formal charge is a better indicator of stability often than just normal gas configuration. I hope that was helpful.